Alright, in this video I want to talk about an immersed pipe in a river. So just imagine you have a river with a free stream velocity and a certain free stream pressure. Okay? It's flowing horizontally and you have a sort of a pipe-like structure in there. You can just imagine this to be a pipe with an orifice plate in there. And it's secured to the riverbed by these supports. And your objective, or the objective of the question, is we want to develop an expression for the flow rate in the pipe. First of all, we will need to have a model for our system. We need to understand our system. Alright? So, flow rate first equals to average velocity times area, the cross-sectional area. And since we are doing it for the pipe, we need to make sure both of these symbols actually refer to the pipe itself. So we have average velocity of the pipe and the area of the pipe. Oh, not forgetting, to simplify our question, we neglect shear forces, entrance and exit effects. Alright, you'll just neglect this. That will be important for our analysis later on. So, getting back to this, we will have flow rate in the pipe will equal the velocity of fluid in the pipe times the area of the pipe. Now the area of the pipe is just simply AC, which is the cross-sectional area of the pipe. So we do know this, we just don't know this. Now how do we find the velocity of fluid in the pipe? And to do that, we need to actually understand our system a little better. Now let's redraw our system again. Again, we have our external flows with the free stream velocity and pressure. We can see that a little better. Free stream velocity and pressure flowing into the pipe. Now what happens as this stream enters this pipe? Obviously you can see that this offers some resistance to the flow, so definitely it may slow down. And as with every orifice plate, as the flow goes from here to here, you'll have a pressure drop. And again, as it exits, well, after the pressure drop's done, the flow will exit and will rejoin with the other flow. And again, we are not sure what exactly happens here. Alright, and this pipe will be experiencing a dynamic pressure of half U infinity V square and static pressure of P infinity. Or rather, we have a stagnation pressure of P infinity plus half rho U infinity square. Of course, we assume a steady flow, incompressible flow, and flow of constant viscosity. We don't actually know how the dynamic pressure actually changes from here to here, but we do know there's a pressure drop here. So that gives us two things to do. One, we need to see how much the pressure is dropping from here to here, because that will be dependent on the flow rate or the velocity of fluid in the pipe. And secondly, we need to see how pressure or the fluid flow properties such as velocity and pressure actually change from here to here, and maybe even here to here. So that that's our focus areas for today. Yeah, for this question anyway. So let's look at focus area number 1. How the fluid changes or behaves when entering the pipe, or maybe exiting as well. Because that will help us understand and derive some equations on what we can do as the fluid enters the pipe. So we can understand how the pipe velocity inside relates to the free stream velocity and pressure. Alright. So we have this kind of a situation and we are not quite sure what to do. So what we can do is actually imagine two simple cases that are perhaps related to this. You can imagine a case where, okay, there's no orifice plate obstruction in the pipe, and the fella's just going to move, the fluid is just going to move freely through the pipe and around the pipe, so there's no obstruction. Second of all, there's a case where the pipe is completely blocked off. Alright? Okay, there's nothing too interesting about the fluid flows here, because it's almost as if the pipe isn't there because we neglect the shear forces. Here, however, we see something a little more interesting. As the fluid flows into the pipe with a static pressure and free stream velocity, infinity, right, you can notice that the fluid actually slows down. It's almost like a pitot tube. You can imagine the fluid's kinetic energy is actually being converted into pressure as the fluid is pressing itself against this blockage in the pipe. So you can imagine a pressure buildup, and the pressure here equals to the stagnation pressure, which is P infinity plus half rho U infinity squared. Alright? Okay, so how does this relate to this? We can first imagine a case where the pipe is completely blocked off, and then slowly you start opening a hole in the middle here. You open the hole gradually and see how the fluid, you can try and visualize how the fluid actually changes its behavior as you start opening the thing up. So, of course, in the first case, the most extreme case, when the whole pipe is actually closed off, you can imagine the fluid actually just flowing around the pipe. And the pressure here will be the stagnation pressure, and so will the pressure be here on the inside. Okay, the pressure here on the inside will be equal to the stagnation pressure. You can imagine the fluid just flowing around the pipe as if it was just a static object. And now, over here, you can imagine the fluid just beginning to converge again. And of course, we don't just expect the fluid to do that. If the fluid is actually flowing fast enough, we may actually have some turbulence here. Now, how do we know that? Well, we can see from experience, or we know that as if we let objects travel through a fluid medium, such as a ball, for example, or sphere. I didn't draw my streamlines properly, but I hope you just get the idea that if fluid is actually flowing fast enough, you will have some turbulence here because the fluid cannot converge back fast enough because by virtue of its inertial forces. It has too much inertia to actually be pushed back here. Well, it has something to do with the Reynolds number, but what essentially happens is that you have two pockets of air or two pockets of fluid going this way, and what happens, I hope you don't mind the drawing, just imagine there's a pocket of air down there or pocket of fluid down there. What you can do is you see this streamline actually imparting some momentum on this fluid volume here. Likewise, you have some momentum imparted here. Let's draw it a little more clear in this diagram. Okay, you have fluid going this way, and the eddy currents or the turbulence is actually going this way. So these guys are just going round and round because of the momentum that's being passed on by this little streamline down here. So as it's doing this turning around, it's actually just dissipating energy and causing a lot of drag, because this is actually a low pressure region and this is a high pressure region. And you can see over here the fluid actually just stops, and this will be the stagnation pressure of the fluid here as it stops at this spherical object, and this over here will be a pressure lower than the stagnation pressure. As of now, we don't really know what that is, but we can see that in general, if there are objects immersed in a flowing fluid, you can see there's a pressure drag that's being exerted on this object. And likewise for our pipe here, we can probably imagine some similar effects. If the pipe, if the river is actually flowing fast enough, and what you can see is some turbulence at the back going from here to here. And just to remind you, this eventually will have pressure U infinity and P infinity. These are free stream pressure, velocity and pressure values. And here we need to know what the pressure is. Now, how do we know that? What the pressure is there? We can assume first that at a far enough point, let's say here, let's say the fluid is quite far away, alright, the pressure here will be actually just P infinity, and I don't know how long that takes to establish, but let's just imagine there's a control volume here, and outside this control volume the fluid is just flowing normally, and we neglect any kind of what do you call that, effects on pressure. To be more consistent, let's just do this. Okay, the streamlines here and here are more or less okay, they're not the same, okay, but let's just imagine this for a moment, this small little volume here. Okay, here we were far enough from the if you actually go far enough from the turbulence area, the pressure that's acting on this turbulence from the right due to the fluid is actually just the static pressure P infinity. Alright, and I don't know what the pressure on the top and on the bottom is, but we assume there's some symmetry, so we can just neglect the effect. But you know it's not moving. This little this little volume of turbulence is just steady down there, as long as the fluid has that fixed velocity and pressure. So since this little area of turbulence or volume of turbulence isn't moving, you must assume there's some force that's actually being exerted here as well. If not, if there's no force here, this pressure will just push this turbulence in. But the fact is, it is at a steady state, so you must assume that if there's a pressure of P infinity here, there's a pressure of P infinity here as well. And if there's a free stream pressure here, it will act on this plate as well. Here will be the stagnation pressure acting here, and here is the free stream pressure acting here. Alright, so I'll stop for now. This is just part 1. In my next video, I want to show you how this can actually apply to our orifice plate problem.